Welcome back. We continue our discussion on intermolecular interaction forces. We talked in the previous class about the total interaction or total potential energy of interaction between two blocks of materials 1 and 2 with thicknesses d1 and d2, where the interaction is only due to the attractive London forces. And this is the expression we have obtained, which let us rewrite, because we will be building our concepts based on this. Let me just caution you, A12 and this 12 has nothing to do in common. This 12 is a numerical prefactor which comes from the integration, and A12 is essentially the Hamarkar constant between blocks of material 1 and 2. Okay. And we also talked about certain limiting cases. For example, if the separation distance between these two blocks is infinity, that is d tending to infinity, in that case GLW tends to 0, or there is no van der Waals interaction because you are in this part of the force curve. Similarly, if d1 and d2 both are very thick, I mean you are talking about the interaction between two semi infinitely thick blocks, then of course you get GLW to be equal to minus A12 divided by 12 pi d square. Further, we talked that we could calculate the change in the potential energy when the two surfaces are brought in contact from initial infinite separation, and essentially what we do, we look at G at d0, that is at contact, and look at the change in the energetics of the system, that is the delta G LW when G is at d0, that is at contact, minus the initial condition, that is G LW at d tending to infinity, and it turns out that the delta G LW is minus A12 divided by 12 pi d0 square. We also understand that this delta G LW 12, if we want to be more accurate, that is two surfaces of 1 and 2 which were initially at infinite separation distance, they are brought in contact. So, we know from macroscopic surface tension this can be considered as gamma 1 to LW minus gamma 1 plus gamma 2, both the LW components. The situations match if there is no other interaction. So, in that case one gets A12 is equal to this. So, if d0 is somehow can be measured, then everything else can be macroscopically measured. We also showed that A12 can sort of take this functional form. These are some of the expressions which we will be needing, and A11 and A22 have these functional forms, and of course, one can show that A12 is under root of A11 into A22. Well, we start to build our concepts from this point. Okay. So, what we need to understand is that this if we now take a relook at this scenario, you have 1 and 2 and they are in air, and you bring them in contact, we have no problem in understanding that G12, if you consider only the LW component, it is fine, it is equal to gamma 1 2 LW minus gamma 1 LW plus gamma 2 LW. Now, if 1 and 2 are same material, then we have gamma 1 2 LW is equal to minus 2 gamma 1 LW, because gamma 1 LW is equal to 0. So, in that case the situation gets transferred to something like this. Now, think of the other scenario. If you have both 1 and 2, now let us think of a scenario where 1 and 2 are initially dispersed in a medium, or dispersed in a medium 3, and then they come in contact. So, here also what happens is delta G 132 is initially, finally it will be gamma 12 minus gamma 13 LW plus gamma 23 LW. Okay. Here also if 1 and 2 are the same material, then we will be left with okay. So, this whatever is the change in this potential energy is due to interaction of two condensed phases or two blocks of 1 due to van der Waals interaction. Now, think of a scenario that, or the other thing can be that if 3 is air, then of course, we get to gamma 13 LW, and this gets back to gamma 1. It is identical to this scenario. Okay. But now, think of another setting, it is the opposite setting of this, that if 3 is non-condensed phase, okay, I will use a fresh sheet. If 1 and 2 are both air or vacuum, and 3 is not a 3 is a non-condensed phase. Let us say liquid. So, what you have which is air, therefore, the gamma delta G LW in this case again turns out to be minus 2, but gamma 3 in this case. Okay. So, what is this? This is essentially the change in the potential energy due to the presence, due to this film. So, this is essentially the free energy of the film per unit area. Or in other words, unlike this situation, where if A1 was a non-condensed phase, we talked about the interaction of molecules across these two phases. So, we talked about the interaction of all the molecules over here with all the molecules over here. But what we did not talk is that if 3 is a non-condensed phase, irrespective of whether 1 is a condensed phase or not, or for every non-condensed phase, we have so far not looked at the self interaction of the molecules. That is, we have taken to put it in simple terms, we have taken two blocks. We go back to the previous derivation, which we have understood in great detail. We have taken two blocks, and the way we did our derivation, we talked about the possible van der Waals interaction of all the molecules of this phase or this block with all the molecules of this block. Okay. So, we did consider only the pairwise interaction of molecules across different block or material. Okay. We never talked or considered the self interaction. That is how the molecules of a single block or a single material or a single object is interacting. So, the self interaction we have not yet considered. Okay. So, the only thing we have considered that there will be an excess potential energy that will be generated or excess potential energy, that is delta G LW, since we have considered the van der Waals component of interaction only if the two blocks are at infinite distance and they are brought to some finite distance h. So, that we can consider or we understand now, but so far we have not considered the self energy, the self interaction energy, which we are going to do now. So, let us look at the self interaction of the molecules. Let us, so we look at the self interaction. Let us say we have a semi infinite block of material 1. Okay. I would also like you to keep this figure intact in your mind, and the expression, corresponding expression for the delta G or the GLW, let us write it down, we will be needing it. So, that expression okay. So, this is something I would like you to keep in mind. Now, coming back to, let us try to identify the component of self interaction. Okay. So, let us say that we have a semi infinite block of material 1, we generate an interface over here at a finite thickness h, and it stretches to infinity. So, it is like you have a block like this, which can be a block of wood, a block of butter, whatever it is. You sort of cut it here, generate an interface, and it remains over there itself. Okay. But what happens now? This has a finite thickness h. This anyway tends to, from earlier the expanse was from 0 to infinity. Now, the expanse is from y equal to h to infinity. Okay. But what you need to understand that this is now at an interface. So, though the same material is at contact, this interface now there is a finite separation distance, and that is d 0. So, this picture now in a way sort of gets transferred to d 1 equal to h, d equal to d 0 and d 2 equal to infinity, and you can immediately draw a comparison between this and this. So, okay. So, I will repeat what I have done. I have taken a block of let us say material 1 which is semi infinite, and at a distance h I have created an interface. So, I have applied some energy. So, the question to ask is let us say you have taken, this is something we have talked in one of the earlier classes when we were talking about surface tension. So, you can just look back to those lectures and find out. I gave you an example that if you have taken a block of butter and then you just cut it, you are supplying some energy from outside. Now, you are neither you are creating any butter nor you are destroying any butter, mass remains conserved. So, why you need to supply this extra energy? Well, you need to essentially supply this extra energy to create these additional interfaces which get generated by cutting. Now, suppose we do the same thing, we cut this block of material over here at a distance h let us say from the top, and we keep it placed over there. So, that is all what we have done. It is the same material, let us say this is material 1, this is material 1, but of course, in order to create this interface you have to supply some external energy, that is something you should not forget. And the other thing is, so earlier the expanse was from 0 to infinity, now the first block is or the thin layer is between let us say 0 to h, and the second layer is from h to infinity. And since you have created an interface, the interface we understand that the minimum separation distance that an interface can assume is d 0. So, we sort of can have a mental image of this system as d 1 equal to h, d equal to d 0 and d 2 equal to infinity. Okay. So, that is what we have. So, now let us say we talk of energy of molecules in the block in the range 0 to infinity is equal to molecules between 0 to h plus h to infinity plus interfacial interaction between molecules confined between 0 h and h infinity at h. Okay. So, all we have done, we have considered, we have just written in simple words the total energy of interaction of the molecules present within this block. That is, now we are talking about the self energy of interaction. When in the earlier lectures we were defining the intermolecular forces, we never mentioned that intermolecular forces has to act across different blocks or different material, that we have never mentioned. So, there is no reason to consider that these intermolecular forces which can span few tens of nanometer across vacuum or air, there will be no interaction between neighboring molecules. So, that is present, and that is what we are identifying or referring to as the self interaction of the molecules. So, what we have done, we have considered the self interaction, we are now trying to identify or get some expression for the self interaction of the molecules, and in order to do so we have just taken a block which is a semi infinite block, and we have sort of cut a thin layer of thickness h at the top, and we have placed it back, left it back on the surface. So, now in simple terms we are looking at the total energy of interaction of the molecules, which was confined between 0 to infinity, and we identify that after we have created the interface, this energy of molecules between 0 to infinity, it is now split into sort of 3 parts. The first one is energy of molecules between 0 to h, then energy of molecules between h to infinity, and then interfacial interaction between the molecules confined between 0 to h, that is this block, which now let us say becomes the block 1 and the remaining part of the block. So, I will not confuse you with by saying that it is 1 and 2, I would probably say 1 a and 1 b, because of the fact the key difference between here and here is that here these two are dissimilar material, which under a specific case can be a similar material, but here they are definitely similar material. Okay. Now, we understand that since this is semi infinite, so the total energy of interaction of molecules between 0 to infinity and h to infinity, they are sort of both infinite and they sort of cancel out. Therefore, what you are left with is energy of molecules zero to h is equal to minus interfacial interaction at h, or very simply one can write the GLW, the potential energy of interaction of the film based on van der Waals interaction. So, GLW film is equal to minus GLW interface. Okay. So, this one can write. Now, we have already, I have already told you that we have the GLW interface, the expression is already available to us, the interfacial interaction based on van der Waals forces, and that is we know that it can be written as, or the expression is okay. And this is for this particular setting, 2 blocks of material 1 and 2 which are separated by d. In our case, we have created the interface over here. So, this is our first block, this is now the 1b or the remaining part of the block. So, this the thickness is h, here is the interface. So, we can write sort of d1 is equal to h. So, if you just turn this picture by 90 degree, then it sort of becomes as if this is h and this is semi infinite block with an interface over here. So, this is the same thing we had this is what we have created. So, this stretches up to infinity, same material of 1. This is the figure we have drawn here. So, I am just trying to give you an analog. This is what we have done. So, we just rotate it like this and then map it onto this figure we already know. So, this is h, this is d 0 and this is now infinity. So, in other words, if you plug in d 1 equal to h, d equal to d 0 and d 2 equal to infinity into this expression, then that will give you the GLW at the interface, which turns out to be 1 by d 0 square minus 1 by d 0 plus h square. And one may also argue that h is much larger than d 0. So, therefore, this second term can be approximated as 1 by h square. So, this is 1 by d 0 square minus 1 by h square. Okay. Now, we have GLW of the interfilm is equal to minus of GLW of the interface, and we now have an expression for the GLW at the interface to be equal to sorry, I just missed it out, it is A11 divided by 12 pi. I just missed out the numerical prefactor with the minus sign. So, it is so we now have an expression for the GLW at the interface, which is minus A11 divided by 12 pi divided multiplied by 1 by d 0 square minus 1 by h square for a geometry like this. So, this is h, this stretches all the way up to infinity, and this is the same material, therefore, we have A11. Therefore, since we are now able to find out an expression for GLW at interface, therefore, we get GLW of the film to be equal to A11 divided by 12 pi into 1 by d 0 square minus 1 by h square. Okay. And now, we also have A11 in one of our previous slides, we have found out that A11 turns out to be equal to 24 pi d 0 square gamma 1 LW. Okay. So, if we substitute that, we get the GLW of the film to be equal to 2 gamma 1 LW minus A11 divided by 12 pi into h square. So, this is a situation where we have a scenario like we have a film of thickness h and which is surrounded by air on both sides. So, it is more like a self standing soap film type of a thing. Now, the total energy of the film, the total energy of the film one can see is a summation of the surface tension term, that is corresponding to 2 gamma 1 comes from this side as well as from this side, and then there is a term which is an excess term. So, A11 divided by 12 pi h square is sort of an excess free energy due to self interaction. Okay. And so, you do not have to consider anything to say that well the total energy ascribed to the interfaces is 2 gamma 1 for a film like this, but what you see here that the total free energy of the film is not 2 gamma 1 LW, but it has an additional term. The more interesting term, so which arises out of the self interaction of the molecule, because we have now considered the self interaction of the molecule, and more importantly this excess free energy sort of tends to 0 as the film becomes thicker. So, one can now try to identify the excess free energy in a film by saying that well that is the excess energy in the film. This is for a film, the energy of film corresponding to a finite thickness h minus the energy of film had it been infinitely thick. So, you see the first term will be 2 gamma 1 LW minus A11 divided by 12 pi h square in the first case, and in the second case the term will be 2 gamma 1 LW minus A11 divided by 12 into you substitute infinity here. So, this term tends to 0, and now as you perform this subtraction, this term also cancels out. So, you are left with this excess free energy to be equal to minus A11 divided by 12 pi h square. So, this is the excess free energy of a film due to its thinness, I would say, because the moment h tends to higher values, this term delta G LW of a film goes to 0, or in other words, so this is a very important concept. So, if you have a thin film, then what happens is that because of the interfacial interaction, that is the self energy of the interactions of self energy of the molecules, you can visualize it like that, or due to the interfacial interaction, the interaction. So, here again you have two interfaces or two surfaces which are separated by a finite distance. So, due to the interfacial interaction, there is an excess amount of energy which is manifested like this, and we will later see that this interfacial excess interfacial energy is key to many settings or many unique properties of a thin film as compared to a bulk block layer. So, the same, instead of a thin film, if the now the layer is very thick, or it's a bulk we consider, then what will happen, h will tend to infinity, and the immediate consequence is the excess free energy tends to 0. So, the other way, nice way or nice convention of identifying a thin film would be a system where the excess interfacial free energy is finite, it is non-zero. So, one can look into it like that. So, physically this term sort of becomes significant for ranges of h varying between up to, let us say, maximum of 100 nanometer, certainly not more than that. Effective interface potential phi LW is defined as rate of change of this excess energy as a function of film thickness, which turns out to be A divided by 6 pi h cube. So, it is the derivative of excess free energy with respect to the thickness, the rate of change of the excess with film thickness. We define the disjoining pressure pi as the negative of this term, the negative of the effective interface potential, which is known as the disjoining pressure. We will look into how a system gets affected based on the disjoining pressure when we talk about the stability of a thin film later. But let us continue our discussion with this self interaction or whatever self interaction. So, earlier we considered a system in which we sort of had a thin layer of H and then it was placed on a block of the same material, but more realistic is a setting where you have a thin layer of, let us say, material 2 on a semi infinite block of material 1. We have talked about for example, spin coating. So, this is exactly what you are likely to create. So, in that case 1 becomes your substrate and 2 is your thin film. Okay. So, in this case, if you look at the GLW of the system, what you get is GLW of the film the substrate plus GLW the interface. GLW of the film you now have two interfaces. One is a surface with air, let us say, which has surface energy of gamma 2. This is now an interface between 1 and 2. Therefore, the total energy ascribed at the interface per unit area is gamma 2 plus gamma 1 2 and the excess free energy, which is A22 divided by 12 pi h square. So, this corresponds to the first term GLW of the film. GLW of the substrate, it is a semi infinite substrate. So, only one of the interfaces are available. So, it is gamma 1 2 minus A 1 1 divided by 12 pi d 1 square. So, let us say this is d 1. We would again like to draw this figure. Here d 1 tends to infinity. So, therefore, this term is cancelled, and the interfacial GLW at the interface is minus A 1 2 divided by 12 pi into, we have already talked about the expression for the interfacial energy, which is the GLW at the interface is minus A 1 1 divided by 12 pi into 1 by d 0 square minus 1 by d 0 plus h square. Of course, here it was earlier case, it was an interface between 1 and 1, therefore, it was A 1 1. Here it is an interface between 1 and 2, therefore, the term gets replaced with A 1 2, but other terms remains the same. So, interfacial width is d 0 square minus d 0 plus h square. d 1 tends to infinity, therefore, all other terms tend to infinity, and this one we argued that h is much larger than d 0. Therefore, this term can be subsequently written as A 1 2 divided by 12 pi into 1 by h 0 square. Therefore, the total GLW of the system, if you add up all these three terms, you find that this as well as this term, they are constant. So, only terms which are non-constants are you will find that it is A 22 minus A 22 divided by 12 pi h square plus A 12 divided by 12 pi h square plus all constants. So, this one is minus A divided by 12 pi h square plus C 1. Therefore, GLW of the system, the excess is GLW at h minus GLW at h tending to infinity. Therefore, if you do the subtraction, you get minus A divided by 12 pi h square, because of the fact that if you do the subtraction from here to here, these terms, the constants, cancel out. Therefore, the excess free energy of the system is given as the minus A e divided by 12 pi h square, where, or I will write it down here, for this particular system where is the effective Hammaker constant and okay, and is in this particular case A is equal to A22 minus A12. Okay. Now, we will soon see that if 1. So, this is the condition we had considered, that we have a film of 2 on a substrate of 1. So, we will soon see that whether if a liquid film of 2 on substrate of 1 remains stable or not will depend largely on the effective Hammaker constant. Okay. We also know that A22 can be written as and A12 can be written as. I would request you to look into the previous lectures to get to these expressions. Therefore, AE is can be written as 12 pi d0 square into 2 gamma 2 LW minus 2 under root of gamma 1 LW into gamma 2 LW, and one can do a little bit of algebraic manipulation of the form add and subtract a gamma 1 LW and a 1 gamma 2 LW comes here anyway, from here anyway. So, this you had 2 gamma 1s. So, what you have is and these 3 in combined will give you under root gamma 1 LW minus under root gamma 2 LW whole square minus plus gamma 2 LW minus gamma 1 LW, and this we know from our previous lectures we have done. This is actually gamma 1 2 LW. So, the expression finally turns to pi d0 square into gamma 1 2 LW plus gamma 2 LW minus gamma 1 LW. Okay. So, this is the final expression for AE in terms of the surface tension and interfacial tension. Now, here I would like to introduce the concept of what is known as the spreading coefficient. Let me just do it. So, in very simple terms, suppose you have a surface, a Bayes surface, which has a surface energy of gamma 1, and you coat a film on top of it of material 2. So, this is the film. So, this has a surface energy of gamma 2 now, but the substrate surface, which had an energy of gamma 1, now gets replaced with interfacial energy gamma 1 2. So, the total energy before was gamma 1, while the total energy after coating is gamma 1 2. Okay. So, the spreading coefficient 21 S21 is defined as the initial energy minus final energy. Okay. So, if you now look carefully, what you have got in the previous expression is nothing but the negative of spreading coefficient 21, the LW component of spreading coefficient 21. Okay. Therefore, we can look at the expression again. It is a very simple concept. There is another parameter that can be defined, that is known as the work of adhesion, also based on similar concepts, which is W A, which is gamma S plus gamma L minus gamma S L, or in this case it will be gamma 1 plus gamma 2 solid, liquid and the interfacial tension. So, this is the work of adhesion. So, which can be sort of regarded as the addition of the total surface energies minus the interfacial energy, but the spreading coefficient is defined as the energy per unit area before minus the energy of unit area after you have coated. So, in simple terms, let us see what it means. It means that if you have a, from simple physical understanding, you can immediately say about the stability of a film. So, what does a negative spreading coefficient mean? Negative spreading coefficient means that you had a surface, bare surface, which was having a surface energy of gamma 1 per unit area, and by coating a film you have replaced that surface with two energy components. Now, one is the surface energy or the surface of the liquid and the interface between the substrate and the film. So, a spreading coefficient, a negative spreading coefficient implies that by way of coating you have actually increased the energy. So, whatever was the total energy before you coated the film and the total energy after you have coated the film, the right hand side is actually higher. So, you have in the process created more energy by coating this film. So, we know that every natural process sort of has a tendency to go towards the energy minimization. So, this of course, by way of coating this particular film, which results in a negative spreading coefficient, you have actually increased the total energy. Therefore, a film that corresponds to a negative spreading coefficient is thermodynamically unstable. Without going into any mathematical derivation, you can immediately say this. Okay. But please do not forget that here we consider only the effect of the surface and interfacial energies. So, what is missing here is the self interaction or the thickness effects are missing. We will come to cover those aspects in couple of lectures time. In contrast, if there is a situation where the spreading coefficient is positive, that is by coating the film, you that implies that by coating the film you have actually reduced the total energy of the system. So, such type of a films are thermodynamically stable, because by way of coating of the film there is a reduction of the energy. So, example of a positive spreading coefficient would be coating of a low surface energy film on a high surface energy substrate. So, ideally this type of a film is thermodynamically stable. We will see there are other parameters also when we discuss thin film instability. In contrast, if you coat a high surface energy film substrate, then it becomes, the spreading coefficient becomes negative and the film becomes thermodynamically unstable. Okay. So, the other thing is that the expression of spreading coefficient, of course, here the way we have derived is we have sort of this correlates to the van der Waals component of spreading coefficient, but important thing to note that spreading coefficient is not limited. The definition of spreading coefficient is not limited to van der Waals interaction. So, you can have the total spreading coefficient based on considering all the components of surface and interfacial tension. Of course, you can consider one of the components independently and can get the individual components of spreading coefficient. So, I would just like to show you how spreading coefficient can also be correlated to the equilibrium contact angle. So, this is what we have, the definition of spreading coefficient. Now, for a liquid which is making a finite contact angle on a solid surface 1, let us say, we have from Young's equation therefore, one can write therefore, one gets an expression for S21 is equal to R2 theta minus 1, or I will write cos theta E. This is the equilibrium contact angle, or one can correlate the equilibrium contact angle as this. And we have already said that we have been able to correlate the effective Hamarkar constant for a system in which a film of layer 2 has been coated on a substrate of layer 1 as minus 12 pi d0 square into S21 LW. Now, in case for the liquid and the solid both are apolar and there is no other components of surface and interfacial tension, then of course, S21 is equal to S21 LW, and then one can write that AE is equal to minus 12 pi d square into S21 LW. So, we already understand a little bit based on the sign or based on the basic physics that how a positive or a negative value of spreading coefficient is going to sort of dictate the stability of your of a film, or sort of influences the stability of a film. We will see that subsequently, and in terms of how the sign of so that implies now that we have already considered here that a positive value of spreading coefficient would result in a thermodynamically stable film. So, if we have the entire spreading coefficient is contributed by van der Waals forces, it implies that the necessary condition for a stable film is A equal to negative, or the effective Hamarkar constant for a system has to be negative. In contrast, we have seen that based on basic thermodynamic consideration, that a negative value of spreading coefficient is likely to result in a thermodynamically unstable film. Therefore, a negative value of spreading coefficient would result in a positive value of effective Hamarkar constant. So, we will revisit some of these concepts in greater detail based on certain other considerations in the subsequent class. Thank you.